Hello all and welcome to Introduction of CFD by Mediocre Tasker. Today we are going to discuss about the basics of CFD. Uh, First speaking about the references, uh, the first one by H.K. Weirsteeg and W.K. Malala it's a book for the bibliography and the practice of numerical problems and the methods that are involved in CFD. The second one is a famous NPTEL lecture by Suman Chakraborty, which gives the detailed lecture about a lot of things in the CFD. It's very useful. And to know about a lot of stuff in general about the what do you call the updates about jobs or solvers or any code that you want to run, or like to look about the new bugs that are fixed in the solvers, you can look about the cfdonline.com. Personally, I would recommend you to go for the ANSYS if you're a beginner, but it's a black box. That means you wouldn't know which equations they're actually solving. I mean, you could select the equations you want, but you wouldn't see the structure of the equations, the coefficients which they are using, the specific wall functions or the dampening function which they are using. And so you just give some inputs and you just get some outputs, but you wouldn't actually know like what sort of equations and the details out of the shape of the equations that are actually being solved in ANSYS. So if you're looking for something for development and uh, getting to know how the CFD solvers work, I would suggest you to first look at OpenFOAM. But basically, start with something very easy like ANSYS or Stasi CM Plus or any other thing that which is mentioned by some of the professionals. And OpenFOAM, you could work on the OpenFOAM with your own solvers or your own codes, and you can couple different solvers and you can check about them in the online. Also, much details about the ANSYS solver named as Fluent, which is a CFD solver, can be looked on in the Fluent tutorial guide in the Google. So good luck. And coming to the basics, let's speak about what's a fluid. So basically, a fluid in the simple terms is like a substance which flows, but when we speak of fluid in the terms of fluid mechanics, it's a fluid or a substance which deforms under shear stress or any other external force. This is a bit scientific terms which will be using or which is used in the community. A simple example is water. So when you pour, it just flows from one object to the other object. That means it's just deforming. Or another example is like it just when you apply some sort of force or like any stress, it just takes up the other shape onto which you're pouring it or onto which you're like moving it. Now, speaking about the statics and the dynamics of a fluid, so static steady is something where the fluid is in equilibrium and you steady the balance of pressure and forces on that equilibrium. In the real-time world, you can look up for the example of submarine or an object that is floating on water. So that gives you a balance of the statics or the forces which are in equilibrium, static equilibrium to be more precise. It means the fluid or the body is not moving, to be more precise. Dynamics of a fluid defines the fluid in motion, like more detailed into aerodynamics and also a lot of other stuff like a venturi meter or something where the fluid flows, and there has been a lot of detailing and also a lot of factors included because the flow of the fluid because of the flow of fluid. And one good example is that of the fluid in an IC engine. It's a four-stroke engine over here, and the mixture of fuel and air is being combusted, and the energy or the heat is transferred outside, and that makes the engine move. Transferred in the sense like the pistons are moved because of the rapid combustion of fuel and air over here, mixing of air over here. So this is one typical case of dynamics of fluid where the fluid is in motion. Now, speaking of Newtonian and non-Newtonian fluids, so in the CFD community, more and more research is being done on the Newtonian fluid because it's a general fluid that is available in the world. For example, water or any other commercial fluids. such as like ethylene or whatever. Like more and more research is being done on the Newtonian part. Also, it's done on the non-Newtonian part, but it's not a good amount of research that's being going on. So speaking of the Newtonian part, the Newtonian fluid obeys the Newton's law of viscosity, that is made up to sense like stress, or like more precisely molecular stress of a fluid is proportional to the strain of a fluid. uh, that can be given from a detailed that can be given from the curve over here, like the shear stress on the x-axis and the strain, or the strain on the y-axis. And you can see over here the black line is a Newtonian fluid, and the others are like the non-Newtonian fluid, where you can observe the phenomenon like shear thickening and shear thinning, and also like plastic fluids over here. So speaking of non-Newtonian fluids, shear and strain proportionality are not linear, or it does not obey the proportionality as that of the Newton's law of viscosity. For example, you can look as that of honey or blood. Blood is a very good example. Speaking of blood, the non-Newtonian nature of the blood gets it from the plasma, so that makes the blood a non-Newtonian fluid, and it makes it very, what do you call, sticky or jelly type of substance, and shear stress is not proportional to the strain rate. So yeah. And speaking about the types of flow, uh, there's a steady and unsteady flow. Like if you speak of the mm, Navier-Stokes equation, so that is the ultimate equation which all or most of the community is working on currently, and they're trying to get analytical solution for that in the three-dimensional form. But it's still being researched on in the current world. So steady and unsteady fluids are something which speak about the dependent of the fluid velocity with respect to time. As you can see over here, like a steady part is the fluid has the same component of velocity uh, described by the vectors over here, but an unsteady part in the future, the velocity gets diminished based upon the size of the vectors over here. Uniform and non-uniform. Uniform flows are something which depends upon the space. The space is meant to say like, for example, over here, the variation of velocity over the direction uh, of which the fluid is moving is same from the starting to the end. That is meant to say like the velocity of the fluid over here at the entrance is same as that of the velocity of the fluid over the exit. So it is said to be an uniform flow. But over here, if you look, a non-uniform flow is such that the velocity of the fluid at the entrance is not equal to the velocity of the fluid at the exit, because as you can see of the uh, area being reduced over here. So if it's a fluid of Mach less than 1, then the velocity of the fluid might increase, and if it's a fluid of Mach greater than 1, then the velocity might decrease because of the contraction and the velocity equation. I mean the relation between the velocity and the area. And speaking about the other types of flow, which are the viscid and the inviscid flow, sorry. So one good example over here, as you can see, is a flow where Mach greater than 1, Mach of flow greater than 1. And as you can see over here, there is an inviscid flow for the Mach which is greater than 1, but across the boundary layer or around the boundary layer of the aerofoil, which is shown over here, there is a viscous flow, and there will be a regions of strong interaction between the inviscid flow and the viscid flow over here. So this is one challenging part for the CFD community, to design the equations or to get the equations of the flow for this inviscid and viscid regions, where it's difficult to interpret their behavior because the boundary conditions so change over here, and also the nature of the equations such as the hyperbolic or elliptic or parabolic being changed over here because of the action of viscosity. So this is one challenging part in the CFD community, to model the inviscid and the viscid interactions. But viscid, to be more clear, said to be depending on the viscous nature of the fluid, and inviscid fluids are such where the viscous nature of the fluids does not act much upon them. And rotational and irrotational fluids, this is one example which I got in the internet about the rotational and irrotational fluids. So in speaking of the mathematical sense, a curl of a vector of, or a curl of a velocity is said to be zero if the flow is irrotational, as you can see over here. But in this example shown over here, it is said that there is no shearing of the element, and also the flow is irrotational, but it is not true in all the senses. Even if the flow is not irrotational, there might be some shear of the flow. If you want to look about more into this, there is something called as a Q criterion, which you would look in the internet, where the positive part of the Q criterion gives the flow to be rotational, and the negative part of the Q criterion gives the flow to be sheared. And zero, if the Q criterion is zero, then there is no shear and no rotation part of the fluid. So this is one of the key aspect which community uses to look about whether the flow is more into the irrotational or the more into shear, or the buildup of the vortices in the rotational part, and so on. You could be looking at it in the internet. And so, as I mentioned earlier, the Navier-Stokes equations, which are the set of continuity and the momentum, so which are the set of four equations for the incompressible Newtonian fluids. So, as you can see over here, these are depending upon the time and also in the space. So, for the steady parts, the equations which are depending upon the time vanishes, and for the unsteady part, they remain over here. But for the uniform part, the equations depending upon the space, for example, the one depending upon say x or like y or z, if they're uniform, so after a certain region of time, like when the flow is fully developed and when it gets uniform, this part get vanishes, depending upon the type of problem. And viscid and inviscid has more to do with the viscosity, so that being modeled over the viscous stresses over here. So the coefficient of the viscous stresses, like this is the molecular viscosity, and rotational and irrotational will be more into the curl of the velocity, and that would be giving you whether it is a rotating or an irrotating flow. Also, speaking of the functions of flow, there is laminar, transition, and turbulent. Yes, turbulent is a function of a flow. That means um, a flow can be turbulent after only it follows a certain criterion. For example, flow around a sphere, or about flow on a linear flat or a flat plate. It can be turbulent after following a certain non-dimensionality criteria, where, as you can see, on flow around a cylinder after crossing Reynolds of around 46 and 47, the flow tends to be turbulent if it's a laminar inlet flow. And flow on a flat plate, which is a very famous case for building up the Blasius boundary layer and all that, tends to go for 10 power 6 of Reynolds number for the case of turbulent, and before that from 10 power 5 or 10 power 4 to 10 power 6 it's transition, and before that it's laminar part. So it's case dependent and it's function of the flow. So that analyzing the turbulent part is very chaotic, because uh, we do not have any analytical solutions to look for the turbulent cases, but we only depending on the statistics of the flows which are unsteady. So we take a ensemble average or ensemble statistics for all of the flow. Transition is not much studied because transitions are very unstable, and they pair up very quickly into the turbulent flows. Transitions can be observed by certain phenomena, such as on flat plate boundary layer you can see the formation of Tolman shielding waves, and they're pairing up into three dimension and horseshoe vortices and their rotation, and finally leading up to turbulent. whereas on the contrary of jets and all, you can see a vortex rolling up and vortex pairing up, and the vortex building into a complex network. So this is something where it depends upon the point of inflection and the point of non-inflection for the inviscid and the viscid flows, which is a bit deeper topic which we're going to discuss later. So this is about the laminar transition and turbulent. And next we look up the CFD settings. So CFD settings, so I would rather just give an introduction about where CFD is used here, but the actual CFD setting lies in the pre-processing solver and the post-processing. But if you look at the CFD setting over here, just like where CFD is used in the industrial experiments where it's expensive, where the experiments are very expensive and it's hazardous, and where there lies no background for the industrial experiments or validation with the previous studies, or where there no previous studies exist for the industries. So CFD or numerical studies performed to validate the results, and applications of CFD are widely seen in the aerospace engineering, such as turbo machinery over here, such as you can see stators and rotors in a turbo jet aircraft engine which are simulated. And also you can see in the wind engineering, which is a very broad and developing area of study now, and nuclear engineering, manufacturing, also additive manufacturing and thermal applications. So speaking of thermal applications, as you can see a simulation over here, it might be a IC chip in a computer, or it might be even the processors in your cell phone or laptop or any such things where the heat management should be studied, and to know how to drain them and make it cool. Also it's a classical over here, it's a classical example on the extreme left side of additive manufacturing over here. And that's it for this slides, and in the following slides we speak about pre-processing, solver and post-processing, and also type of numerical methods, finite difference and finite volume, and also pseudo-spectral method. And we look about the derivation of continuity and momentum equation, which are the Navier-Stokes equations as I mentioned earlier. So thank you, and I hope you have a good day.